So hopefully everybody saw the email, but we graded homework 1 Monday night. We uploaded the graded version of your homeworks. We just put comments inside the Word or PDF files along with copies of the solutions. As I said, there's a couple people who haven't turned them in, so that's why I haven't posted the solutions publicly. So don't go emailing them to all your friends unless you know that your friends have turned them in already. And homework 2 is due on Friday. I mean, there's the week grace period, so don't worry about it too much. If you're having trouble with R, don't tear your hair out too much. You're welcome to send me an email rather than banging your head against the wall for hours, and I can try to figure it out. And there's also the discussion section on Friday specifically for R issues. I know as first homework can sometimes be annoying that way, so try to minimize the amount of pain. Don't hesitate to email me if it's giving you issues. Well, anyway, for today, doing 2 sample t-tests, generalization of what Erica talked about on Monday. In a 2 sample t-test, it's what Erica discussed was the 1 sample t-test where you have a set of data, you want to test the null hypothesis, the mean is equal to some specified value. A 2 sample t-test is you have 2 sets of data and you want to test the null hypothesis that the mean is the same in the 2 data sets. You have a treatment group and a control group. You want to test the null hypothesis that they're the same, or you have diseased tissue and healthy tissue, want to know if gene expression levels are the same across the 2 tissues. In practice, in my experience, this is far more commonly used than the 1 sample t-test. In fact, I find I almost never use the 1 sample t-test, but I use the 2 sample t-test all the time. So today we will discuss that. So examples of 2 sample t-test. Say you have a cholesterol drug, you want to test the null hypothesis, there's no difference between your new drug and the placebo. Or say you have a growth hormone that you're applying to mice, want to see if test the null hypothesis that the growth hormone doesn't work, that they grow at the same rate as regular mice versus the alternative, that they'll be heavier. Or say you have samples of metastatic and non-metastatic breast cancer, you want to identify genes that may be associated with metastasis. You want to test the null hypothesis of no difference in gene expression levels between the 2 samples. So, as you'll recall from the past few lectures, and once again I apologize for the fact that Keynote is making the bars disappear on all my x's, that if you know the population standard deviation sigma, you can do hypothesis tests about the mean mu by taking advantage of the fact that the sample mean minus the population mean divided by the population standard deviation divided by the square root of the sample size will have a normal distribution with mean 0 and standard deviation 1. So a test statistic for testing hypotheses about the null distribution, you just plug in your hypothesized value of mu 0 into this equation. If you get a test statistic that's too large or too small, then you can reject the null hypothesis of that the true mean is equal to mu 0. And the big drawback to this approach is it only works if the population standard deviation is known. In practice, it never will be, so this approach has limited utility in practice. So what we usually use instead is the t-test, which is really similar, but rather than taking x bar minus mu divided by sigma over root n, we take x bar minus mu over s divided by root n, where s is the sample standard deviation, and that has a t-distribution with n minus 1 degrees of freedom. The advantage of this over the z-test is that this works even if the population standard deviation is unknown. Once again, if we hypothesize the mean is 0 or the mean is 20 or any specified value, you just take the sample mean minus 20 divided by s over root n, see if you get something that's too large or too small. Now, to extend this to this two-sample case, the simplest way to do this is if you have a matched pairs design, which typically means that the way you would get data in a matched pairs design is typically you would take a measurement at the beginning of your study, apply some type of treatment, and then measure it again after the study. Or you might apply two different treatments to the same subject or to closely paired subjects or something like that. And essentially, what the matched pairs t-test does is you take the before measurement, subtract off the after measurement, and then do the one sample t-test. That's really all there is to it. And then you test the null hypothesis that this difference is equal to 0. If the null hypothesis is true and the pre-treatment mean is the same as the post-treatment mean, then the mean difference between the two values should be 0. If this difference is significantly different than 0, then that implies that the treatment had some sort of effect. Instead, it's exactly the same test statistic that you use in the one sample case. So, this is more data from a student in this class a couple years ago. She was measuring ATP levels in several mice. They were treated with WY14643, which I have no idea what that is. Maybe some of you do, but it's something that could possibly have affected their ATP levels. So she wanted to test the null hypothesis that the ATP level stayed the same after being treated with this particular chemical. So I think I remembered to post this data set on Sakai if anybody wants to try this, but it's a small data set. It's just a spreadsheet with 12 rows, 2 columns. First column is the pre-treatment ATP levels. The second column is the post-treatment ATP levels. And we want to test the null hypothesis that the ATP levels post-treatment are the same as the ATP levels pre-treatment. Read the data into R with read.csv. The data set looks like this. So, there's several ways that you can do this. There are several ways that you can do this one sample t-test, or this matched pairs t-test in R. The most painful way that you probably will do rarely, if ever, in practice is to use the pt command. This code here gives the syntax for how it works. Basically, I define this variable ATP.diff to be the difference between the pre-treatment ATP levels and the post-treatment ATP levels. Recall that in R, if I use the syntax ATP square bracket comma 1, that gives the first column of this data frame. And if I go ATP square brackets comma 2, that gives the second column of this data frame. So I go ATP bracket comma 1, it will give me this column. ATP bracket comma 2 gives me the second column. When I subtract one from the other, I just get the pairwise differences between these two columns. So the first element of the difference will be 13.73 minus 10.19 and 14.33 minus 10.61 and so on. I'll have, if this ATP.diff will give me a vector of length 12, that's the pairwise differences between each of those sets of measures. And so I have this vector ATP.diff that's a vector of length 12, consists of the difference between the pre-treatment and the post-treatment ATP levels in each mouse. So what I do is I calculate the test statistic. In this case, I'm taking the mean of the differences minus the hypothesized difference, which in this case is 0. So the numerator would just be mean ATP.diff minus 0, which is of course just mean ATP.diff. Then the denominator is I take the standard deviation of the difference divided by the square root of the sample size. Sorry. I think the warmer weather, my allergies are out in force now. But that gives me the test statistic. Remember, under the null hypothesis, this test statistic should have a t-distribution with 11 degrees of freedom. To get a p-value associated with a specific test statistic in the t-distribution, I go pt of the value of the test statistic, 11 degrees of freedom. And since I want a two-tailed test, I subtract this from 1, multiply by 2, I end up with a p-value of 0.002. Don't worry if you didn't follow all that, that's just for illustration purposes to show that when we use the slicker formulas we get the same results. That's how you do it, computing the test statistic directly. In practice, there's other commands that are easier to use. For example, the command t.test that Erica discussed on Monday, recall if you just say t.test without giving it any parameters, it will give you a test of the null hypothesis that the input vector is equal to 0. So we say ATP.diff, and as against the alternative hypothesis, the true mean is not equal to 0, we get a p-value of 0.002, exactly the same as what we got computing the test statistic directly. And that's probably less painful than calculating a test statistic and using PT and figuring out if you multiply by 2 and all that. If you use t.test, it will do all this for you automatically. And recall from Monday that if you just say t.test of x without giving it any parameters, it will do a two-sided t-test to test the null hypothesis, the mean 0, which in this case is exactly what we want. The only caveat is that you still have to compute this intermediate variable ATP.diff, which I mean isn't that hard to do, but it is one extra step. The other way that you can do this that doesn't even require you to compute the intermediate variable is, as I said before, the t.test command is quite versatile. It's smart enough that rather than giving it a vector of differences, you can just give it the two columns of this data frame. Say t.test, I want to compare the mean of this vector, i.e. the pre-treatment ATP levels, to the mean of the second vector, i.e. the post-treatment ATP levels, and then I add this parameter paired equals true, which tells R that I want a paired t-test. If you don't specify that it's paired, it will give you an unpaired test that I'll describe here in a minute. But as you can see, once again, I get p equals 0.002, the exact p-value that I got using the other two approaches. The advantage of this approach is that you don't have to create the intermediate vector of the pairwise differences. And as I said, in general, if you go t.test x comma y paired equals true, that will tell R to do a paired two-sample t-test, subtract the first element of y from the first element of x, subtract the second element of y from the second element of x, and so on down the line. And it'll test the null hypothesis this vector of differences is equal to 0. And you need to add this extra parameter paired equals true, or it will do an unpaired test, which I'll describe here in a second. And as I've told you before, in general, if you go x square bracket comma 1, that will give you the first column of X, i.e. the pre-treatment ATP levels in the early example. If you said X square brackets 1 comma, then that'll give you the first row of X. And if you're not totally sick of alternative ways to calculate this t-test, there's one other way that you can calculate this t-test that's sometimes useful if you have your data stored in a slightly different format. Let's say that if rather than having a spreadsheet with one column that was pre-treatment and a second column that was post-treatment, let's suppose that all of your ATP levels are in one column, then you have a second column that indicates whether they were in the pre-treatment group or the post-treatment group. This will, a lot of times you'll get data sets in this format, particularly if you have, particularly for large studies and things like that. You may not want to copy and paste these numbers in R or mess around with it to reformat it to the form that T.Test wants. Luckily, T.Test is smart enough to be able to handle data of this format as well, as I'll show you here in a second. In this case, first thing I do is I attach this data frame ATP2 just so I don't have to go ATP2 $ATP and ATP2 $treat. This saves a little bit of typing. And this time I say T.Test ATP twiddle treatment paired equals true. And see, once again, I get exactly the same p-value of 0.002. As you'll recall, this when you use this little twiddle in R, that's a formula object. We've seen this once before when we were computing the side-by-side box plots. As you'll recall, that if we wanted to compute a box plot of the pre-treatment data versus the post-treatment data, we could have said box plot y twiddle x. Now, in this case, we're using the same syntax for t-test. We say ATP level twiddle treatment group. In general, this formula object means that you're trying to predict y based on x. In this specific case, we're saying we're trying to predict the ATP levels based on whether it's pre-treatment or post-treatment. And as I warned you before, this formula syntax you'll see several times in this course. And the one this can be convenient if your data is in the format that I described on the previous slide. The one caveat here is that you have to make sure that your data is in order if you use this syntax, that it will if x is, well, first of all, x has to be a factor with exactly 2 groups. You can't do a t-test to compare 3 or more groups, so R will blow up if x isn't a factor with 2 groups. And your data also has to be in order. In other words, the first row where x is equal to 1 has to correspond to the first row where x is equal to 2, and the second row with x equals 1 has to correspond to the second row with x equals 2, and so on. In other words, in this particular data set, the first row where treatment equals pre has to correspond to the same rat where treatment equals post. The second row where treatment equals pre has to correspond to the second row where treatment equals post. Make sure your data is in order if you do this. In practice, it's not common to use this syntax if you have a paired test, but this can be very handy if you have an unpaired test, so I'll describe here in a second. The general 2-sample t-test can, as its name implies, can be used in a more general case. The matched pairs two-sample t-test only works if you can match each subject in the first group to a corresponding subject in the second group. If no logical pairings exist, or if the sample sizes are different, then you need a two-sample t-test. And personally, I'll use the paired t-test occasionally, but the unpaired test tends to be far more common. If you have a set of people with a disease and a set of people without disease, no matching to one another, then you'll want to just use the two-sample t-test to compare the two groups. And first of all, the assumptions for the two-sample t-test. You have to assume that you have two distinct populations that you're drawing from, and you also have to assume that not only are the observations in the first population independent of one another and the population in the second population independent of one another, you also have to assume across populations they're also independent. Now, in a paired test, these responses are not independent. In fact, there's some definite dependence that if you measure the ATP levels in a rat pre-treatment and the ATP levels in a rat post-treatment, then you would expect that the pre-treatment level is not going to be completely independent of the post-treatment levels. If they were high pre-treatment, they'll probably be high post-treatment. In the general two-sample t-test, you have to assume that all the data points across groups are independent of one another. So, in a two-sample t-test, some notation here. Basically, say you have a treatment group and a control group. We'll assume the treatment group has N1 observations and the control group has N2 observations. And once again, my bars disappeared in Keynote. We'll assume that the sample mean for the treatment group we call x1 bar, sample mean for the control group we call x2 bar. Likewise, S1 and S2 are the sample standard deviations. Mu1 and mu2 are the unknown population means. Sigma 1 and sigma 2 are the unknown population standard deviations. Now, to calculate the distribution of these sample differences, don't worry too much about the details here. This is mostly for your information, that basically we want to estimate the difference between the population means, namely mu1 minus mu2. We'll almost always want to test the null hypothesis these two means are equal, i.e. that this difference is equal to 0. Very occasionally you might want to do something different, but for almost all examples you can assume that this is 0. Oh, if you'll recall some of the formulas I gave in previous lectures, the expected value of the difference between x1 bar and x2 bar is just the difference between the expected value of x1 bar minus the expected value of x2 bar, which of course is just mu1 minus mu2. Similarly, the variance of the differences, if we assume they're independent, will be sigma 1 squared over n1 plus sigma 2 squared over n2. If you don't remember how I calculate that, don't worry about it. For this class, it's not that important. So, a two-sample Z statistic, which I'll put on this slide and you can promptly forget because it's just as useless as the one-sample Z statistic. But if you know sigma 1 and sigma 2, then this test statistic, the difference in the means minus the hypothesized difference in the population means divided by the square root of the variance differences is normal 0, 1. As I've said before, this only works if you know the values of sigma 1 and sigma 2. In practice, you never will, so this is more or less useless. So what you will use instead is the two-sample T statistic, which is the same idea as the one sample T statistic, it's the same as the Z statistic, only rather than using the unknown sigma 1 and sigma 2 down here, use the sample standard deviations in the denominator of this fraction. The advantage being that in general you won't know sigma 1 and sigma 2, but you can estimate S1 and S2 using the data, so you can calculate this even if the population standard deviations are unknown. The one wrinkle here is I just say t distribution with k degrees of freedom. What's k? Well, in general, it turns out this test statistic I described on the previous slide doesn't actually have a t distribution, even if the populations are exactly normally distributed. There's a few special cases where it will, but in general it won't. Luckily, it's close enough to a t distribution, so the fact that it's not exactly a t distribution doesn't really matter. In fact, later in this class we'll discuss some approaches that don't assume the t distribution at all, and in my experience they virtually always give almost exactly the same results as this approximate t distribution. And you'll notice that I didn't specify the number of degrees of freedom for the t distribution in the previous slide. That's because the formula for the degrees of freedom is kind of a horrific mess. In practice, I'm just going to say don't try to calculate this on your own, just use t.test in R. I mean, there's some approximations that you can use in practice that are usually pretty good, but I mean, R will do it for us. There's just no reason to torture yourself with it. And as I said before, under the null hypothesis, in practice, you'll almost always assume that mu1 equals mu2. In other words, the means of the two populations are equal to one another. But if for some reason you wanted to test the null hypothesis, the difference in the means were 10 rather than 0, you could still do that. So an example is of two sample t-tests, the plant growth data set in R. If we've used this for a couple other examples, recall that in this experiment there were 30 plants that were assigned to one of three groups, two treatment groups and a control group. And we want to test the null hypothesis that neither of the treatment groups are significantly different from the control group, versus the alternative that one or both of the treatments either increase or decrease plant growth. Oh, I think I showed this example when we were discussing box plots, but if you do a box plot of the plant growth data, which is an aside, is a good idea to do anytime that you're analyzing a new data set, just so to get like a 10,000 foot overview of what's going on and to look for any sorts of suspicious data. We see some evidence that the first treatment group may decrease plant growth and weaker evidence that the second treatment group may increase it slightly compared to the control group. And we don't see any major problems with skewness or outliers. I mean, using the 1.5 IQR criteria, there was a very mild one there, but I mean, it's nothing that jumps off the page at us, so we conclude it's probably safe to use the t-test despite the relatively small sample size. So the commands to perform this t-test in R, I use t.test again. First of all, I attach the plant growth data set. This data set is built into R, so you don't have to read it from a CSV or anything. Then I go t.test of weight. This plant growth data set is a data frame with two columns. One is a column called weight, which consists of the 30 weights of plants. The second is a variable called group, which is either control treatment 1 or treatment 2. So the first thing I do is I use t.test to test the null hypothesis of no difference in the weights between the control group and treatment 1. And I get a p-value of about 0.25. So in this case, we fail to reject the null hypothesis of no mean difference. In this case, I mean, we have a sample of size 10. It's possible that we're failing to reject just because our sample size is too small. So if you looked at the box plot, it did look like the treatment 1 group had lower means, but there isn't enough evidence to reject the null hypothesis at the p equals 0.05 level for this particular data set. And in general, if you say t.test x comma y, that'll do a two-sample t-test, test the null hypothesis, the mean of x equals the mean of y. Note that this time I don't say paired equals true. If you don't specify that you want a paired t-test, by default R assumes that you want an unpaired t-test, which is much more commonly used than the paired ones. And also, if you don't specify a mean difference, it assumes that you want to test the null hypothesis that the difference is equal to 0, i.e. that the means of the two populations are equal to one another. So the vast majority of the time in practice, that is what you want. And another R syntax note that you may not have seen before on the previous slide. No, I said weight, and then in square brackets, group equals control weight, and then brackets group equals treatment. What that says is I want only the elements of weight where the group variable is equal to control. In other words, it pulls out the 10 controls and gives you a vector of length 10 and gets rid of the remaining weights. Likewise here where I say weight, square brackets, group equals treatment 1, that gives only the treatment 1 people. So that's a little funky R command, but it is very useful in practice. That, for example, on the second homework assignment, if you're tearing your hair out over the medical subjects one, aside from if you need to select a subset of a particular data set, I mean, one way you can do it is just go into Excel and copy the rows that you want and create a new spreadsheet that way. That works. The other way you can do it is with this syntax here. Say, in like the medical subjects, you could go medical subjects in square brackets, gender equals male or something like that, and it will give you only the rows of the data set where gender is equal to male. Oh, now to test the other two null hypotheses of no mean difference between the control group and the second treatment group, you can do the same sort of thing, t.test weight, group equals control weight, group equals treatment 2, and in that case, we get a p-value that's marginally significant at the 0.05 level, suggesting that the second treatment does increase plant growth ever so slightly. I mean, look down here, mean difference. I think this is weight in pounds or kilogram. I don't know what the weight's in exactly. It's a half a unit. I mean, p equals 0.0479, given the small sample size, is reasonably impressive. As Erica mentioned on Monday, oftentimes the p-value is a measure of the sample size as much as anything, that if the mean difference between two variables is small, the p-value will be borderline for a small sample, but will be very highly significant for a large sample. So in this case, I mean, I don't know that I would want to bet the farm on it, but when we see a mean difference like that that's significant despite a small sample size, you can probably think, okay, most likely it's doing something. And if we compare the treatment 1 and treatment 2 groups, we get a slightly larger or slightly smaller p-value of about 0.01, suggesting that treatment 2 is more effective than treatment, results in higher growth than treatment 1 way or another. And so when would you want to use two-sample t-tests? When would you want to use matched paired t-tests? It's really closely related to the idea of blocking that we discussed in the context of experimental design. The basic idea is that if each element of the first sample can be paired to a similar element of the second sample, then the matched paired design should in principle give you better power than the unmatched design. But if you do inappropriate matching, you can lose power or get inaccurate results. Likewise, if you use an unpaired test when you should be using the paired test, in theory, the unpaired test would give you invalid results because you're assuming the observations are independent when they're actually not. I found in practice it usually doesn't make that big of a difference and you'll usually get away with it. But in general, if there's some logical pairing between the items in the first sample and the items in the second sample, it's better to use the paired t-test. Said the most common situation is like you measure a certain variable pre-treatment, you measure the variable again post-treatment, something like that. In that case, you would probably prefer the paired t-test. So, if we go back to Valerie Soldato's ATP data, we saw before if we do the paired t-test, we get a p-value of 0.002. If we just say t-test comparing the pre-treatment and post-treatment ATP levels, ignoring the pairing, we get the same finding. In fact, we get an even smaller p-value, which is kind of strange. That usually, if you ignore the pairing, your power is worse, not better, but obviously there are counterexamples, and in this case, this p-value is probably overly optimistic because, as I said, the unpaired t-test assumes the observations in group 1 and group 2 are independent, which in this case they almost certainly are not. So, I mean, again, it's very rare to find cases where the results will change drastically, but in this case, using the unpaired t-test would technically be wrong because the independent assumption isn't satisfied. And as I mentioned earlier, if you use the format t.test y twiddle x, that only works if x has exactly two levels, pre-treatment and post-treatment, case versus control, or something like that. In the plant growth data, we couldn't just say weight twiddle group because there were three possible values of group, namely control treatment 1 and treatment 2, which is why I had to do the square brackets, group equals control, group equals treatment 1. With Valerie's data on this slide, I could have said like t.test, ATP, square brackets, treat equals pre, comma, ATP, square brackets, treat equals post. That would have given me the same results. But you can save yourself a little typing if this treatment group is the factor with only two levels. And a couple things to keep in mind in terms of experimental design. You can show mathematically, I won't bore you with the details, but you can show that the closer the sample sizes in the two groups are to being equal to one another, the better the power of your test will be for a given sample size. In other words, if you have if you have enough money to collect 100 samples, you'll get the best power if you have exactly 50 in the treatment group and 50 in the control group, for example. So if it's under your control, the best design is to try to have approximately an equal number in the two groups. Now, in practice, you won't always be able to do that for various reasons. I'm working on a study right now, a case control study, where we have 3,200 controls and less than 200 cases. Now, it's an inefficient design for a case control study. If we would have just had 200 controls and 200 cases, we would have gotten about the same. The reason we did it that way is because there was also a longitudinal component of this study. We're following the controls to see how many of them become cases over time. But in general, if you only have money to collect 100 samples, for instance, it's better to collect 50 cases and 50 controls than it is to collect, say, 90 controls and 10 cases. You'll get better power if the two groups are have approximately equal sizes. And I'll mention in passing that if for some reason you know that the variances of your two groups are equal, you can get slightly better power by telling R that the variances of your groups are equal by adding this parameter to t.test var.equal equals true. In practice, my suggestion is to simply never do this, because you can virtually never be certain that the variances are actually equal. If they're not equal and you do this, you can mess yourself up really badly, and even if they are equal, the increase in power is very tiny. So to me, it's just not even worth opening that can of worms. I never use that particular parameter. I'm just mentioning this because there have been a number of cases in the past where I teach something in this class that I say to never do, and then I get an email from somebody saying their PI wants them to do it anyway, so I put these things on the board in case you're ever asked to do it. But for this class, I'm never going to ask you to do that. In fact, I strongly encourage you not to do that. And also note in passing that you can construct confidence intervals for the differences between means in a two-sample test, just like we did in the one-sample case. I won't bore you with all the details, because R will do this automatically. If you noticed, in each of the outputs from t.test, it gave a confidence interval for the difference in the means, in addition to the p-values. And my personal opinion is if you're writing a paper or whatever, if you report a p-value, you should always report confidence intervals as well. Confidence intervals, in my opinion, are much more informative than p-values. They get underused, whereas p-values get overused, and people obsess with this 0.05 cutoff for no good reason. So for this class, if you report a p-value, please report confidence intervals as well. And when you write papers in real life, I strongly urge you to do the same thing. And caveats about hypothesis tests that we've been over before. Same sort of thing in the one sample case. You need both samples to be representative of the population of interest. If your samples are biased, then your test results are going to be invalid no matter what. The observations should be independent, with the exception of the matched pairs test, in which case the two items in each matched pair are not going to be independent. And if your sample size is small, they should be approximately normally distributed. Where you usually get into trouble is if you have a small sample size plus really bad outliers or really bad skewness or something like that. But I mean, as I said before, it's rare for you to get in too much trouble because of non-normality assumptions. In my experience, even when the assumptions are clearly violated, usually the p-values you get will be approximately correct. So, things to remember for today: t-tests, you can use to test the null hypothesis the means of two sample are equal. If you can do pairing, you can do the matched pairs test. If there's no obvious matching, then you can just use the standard 2-sample t-test. You want to make sure that your assumptions are satisfied and that you report your confidence intervals. And here's the R commands for today to how to do all these things. Any questions about any of this, homework, whatever? Okay.